Hello, welcome to the course SJPHY2B02 Mechanics 2. The contents of this course is taken from An Introduction to Mechanics by Kleppner and Kolenko. We will continue to discuss topics from Module 3, Harmonic Oscillator. In the last class, we discussed about a damped harmonic oscillator, where we have seen that there is a dissipative force or a damping force which acts against the motion. Consequently, the system continuously loses energy, and there are three conditions: overdamped and critically damped, where there is no oscillation, there is an exponential decay of the amplitude, and only in the third condition, the underdamped condition, you have some oscillation happening in the system. But this is very different from that of a simple harmonic oscillator for two reasons. First one, the amplitude is no more a constant, it exponentially decreases as shown in this equation. Secondly, the frequency of oscillation omega 1 is going to be less than that of the undamped oscillator omega naught. And what about the energy? In the case of a simple harmonic oscillator, we know that since the only force acting on the system is a conservative force, because there you only have the spring force or the restoring force, which is a conservative force, and consequently the total energy is a constant, right? Now here, in addition to the conservative force, we have a frictional force, which happens to be a non-conservative force. So from last semester, we know that the work energy theorem for a non-conservative force field is given by EB minus EA equal to WBANC. So here we are talking about a particle which moves from initial point A to final point B. So EB is the final energy and EA is the initial energy, and WBANC is the work done by the non-conservative force to move the particle from initial point A to final point B. So let's write down the work energy theorem for a damped harmonic oscillator. So imagine that you have oscillation taking place from time 0 to time t. So initial energy is E of 0, final energy is E of t, and the non-conservative force here is the frictional force. So I can write the work energy theorem as Et minus E0 equal to W fric, where W fric is the frictional, the work done by the friction force from time 0 to time t. And if I rewrite this equation, I can write E of t equal to E of 0 plus work done. But total energy E of t is a sum of kinetic and potential energies K of t and U of t. So I can write E of t equal to half mv square plus half kx square. Now what is the work done by the frictional force? So remember, the frictional force is a dissipative force which opposes the motion, right? F is equal to minus bv. So definitely it's going to decrease the energy. Dissipative force means it creates a loss in energy of the system. So the energy is going to decrease. And what is the expression for the energy or the work done? W is going to be integral x of 0 to x of t f dx. Instead of dx, I can write v dt. Consequently, the limits of the integral change from 0 to t. Substitute for f, so this is minus integral 0 to t bv square dt. So I have a negative sign here. So work done or the corresponding energy is going to be a negative energy. Now I can qualitatively say what happened to the total energy, because look at the expression, total energy is E of 0 plus work done by the frictional force. E of 0 is a constant, right? This is the initial energy for a given system. This is a constant. So this is going to depend entirely on the work done by the frictional force, which is a negative work done. And if you look at this expression, as time increases, the negative work is going to increase. So you can see that the negative energy increases. So what happens to total energy? It is going to decrease as the time progresses. So E of t decreases with the time because the friction force continuously dissipates energy. Now what is the exact expression for E of t? We know that E of t is a sum of K of t, the kinetic energy, and U of t, potential energy. So let's now find out the the expressions for kinetic and potential energies. Kinetic energy is half mv square. We need to first find out velocity v. So for that, we can use the expression for x as a e to the power minus gamma by 2t cos omega 1t plus phi. We had to write this expression in the previous class. And velocity is rate of change of position dx by dt. So simply apply the product rule, first term into derivative of second term plus second term into derivative of first term. So a into a is common, take it outside. A into first term e to the power minus gamma by 2t into derivative of cosine is minus sine omega 1t plus phi into omega 1. Similarly, the second term cos omega 1t plus phi into derivative of the exponential term. So this is minus e to the power minus gamma by 2t into gamma by 2. Some terms are common, e to the power minus gamma by 2t into minus 1. So this term is common, take it outside. So minus a e to the power minus gamma by 2t into omega 1 sine omega t plus phi plus gamma by 2 cos omega 1t plus phi. We can also take omega 1 outside, even though this is not a common factor. If you take it outside, we can have a familiar factor inside the bracket. So I take omega 1 outside. So minus omega 1 a e to the power minus gamma by 2t into sine omega 1t plus phi plus half gamma by omega 1 cos omega 1t plus phi. So this term gamma by omega 1 is a familiar factor, right? So in the case of heavy damping, gamma by omega 1 is very high. In the case of light damping, this is very small, right? So let's now specifically take the case of a lightly damped oscillator. So as we discussed in the previous class, there gamma by omega 1 is going to be much smaller than 1. So essentially I can neglect the second term because this factor is going to be negligible. So v is going to be minus omega 1 a e to the power minus gamma by 2t sine omega 1t plus phi. So once I get the expression for velocity, now I can find kinetic energy as half mv square, which is half m omega 1 square a square e to the power gamma t sine square omega 1t plus phi. Potential energy is straightforward. U of t equal to half kx square. We know the expression for x. Take the square of that, multiply with half k. You get u of t equal to half k a square e to the power minus gamma t cos square omega 1t plus phi. The total energy E of t is k of t plus u of t. So half a square e to the power minus gamma t is common, so I take it outside. So half a square e to the power minus gamma t m omega 1 square sine square omega 1t plus phi plus k cos square omega 1t plus phi. We can simplify this even further because we know that the frequency of the damped oscillator and undamped oscillator are connected through the relation omega 1 equal to omega naught square minus gamma square by 4. From this I can write omega naught square equal to omega 1 square plus gamma square by 4. Take omega 1 square as the common factor outside. So this is omega 1 square into 1 plus gamma square by 4 omega 1 square or 1 by 4 gamma by omega 1 whole square. Once again, for the case of a lightly damped oscillator, gamma by omega 1 is much smaller than 1. So you can neglect the second term. So omega naught square is approximately equal to omega 1 square or omega naught equal to omega 1 in the case of a lightly damped oscillator. So we know that omega naught is square root of k by m. So now I can write omega 1 also equal to square root of k by m, or k equal to m omega 1 square. So in this expression, instead of k, now I can write m omega 1 square. So the total energy now becomes half a square e to the power minus gamma t into k sine square omega 1 t plus phi plus k cos square omega 1 t plus 5. K is common, take it outside, sine square plus cos square equal to 1. So E of t equal to half Ka square e to the power minus gamma t. You can simplify this even further, because at time t equal to 0, you say E of 0 equal to E naught, the initial energy. So what is E naught? Simply put t and time t equal to 0 in this equation, e to the power 0 equal to 1. So E naught equal to half Ka square. So instead of half Ka square in this equation, you can write E naught. So your expression for the total energy now becomes E of t equal to E naught e to the power minus gamma t. So for a given system, E naught is a constant. So the behavior of the energy is entirely dependent by this exponential function. This is an exponentially decaying function. So energy of a damped harmonic oscillator decreases exponentially in time. So if you draw this graph, so you can see the maximum energy is the initial energy E naught, and from there it exponentially decreases and finally becomes 0. So consequently, the amplitude of oscillation also decreases exponentially and eventually it becomes 0. So in the case of a heavily damped system, the energy loss is going to be very, very high. So it decays very fast. And in the case of a lightly damped system, the energy loss is going to be low. So it decays slow. So how do you quantify the rate of decay? So for that you can use a parameter known as damping time or characteristic time tau. So tau is defined as the time required for the energy to drop to 1 by E times its initial value. Okay. So its original value is E naught, and time taken for it to drop to 1 by E. 1 by E is 0.368. So time taken for the energy to drop from E naught to 0.368 E naught. So in this graph, this is the time taken. So this is the characteristic time. Okay. Now let's find an expression for tau. So we know that in this expression you substitute for t as tau, so E of tau equal to E naught e to the power minus gamma tau, and we know that this is equal to 1 over E times E naught. So E naught cancel, you have exponential term on either side, so you can compare the exponents. So gamma t equal to 1, from there I can write tau equal to 1 over gamma, and gamma is b by m, so tau equal to m by b. So from this equation it's clear that when gamma is high, tau is going to be small. So in the case of a heavily damped system, gamma is very high, tau is very small. Tau small means the energy dissipates very quickly, very fast. In the case of a lightly damped system, gamma is very, very small, so tau is very high. Tau is high means the energy is going to decay slowly. So now let's take the extreme case of extremely light damping in a system. So gamma is almost 0, gamma tending to 0, so tau tends to infinity. Now, what's the meaning of tau tending to infinity? It takes infinite time for the system to decay its energy from maximum value to this point. Infinite time means essentially there is no decay in the system. The energy is effectively a constant. So in the case of extremely light damping, the energy is almost a constant. In other words, the system behaves like an undamped oscillator. You can also quantify the degree of damping happening in a system using another parameter known as a quality factor or Q factor. So this is a dimensionless parameter which is defined as energy stored in the oscillator divided by energy dissipated per radian. By energy dissipated per radian, we mean the energy lost during the time it takes the system to oscillate through 1 radian. So as you can see, if you take any sinusoidal function, so this is the time period, time required to complete 1 full cycle. So during the time period, the system oscillates through 2 pi radians, right? And in terms of frequency omega 1, I can write time period capital T as 2 pi by omega 1. So capital T corresponds to 2 pi radian. So 1 radian corresponds to T by 2 pi or 1 over omega 1. So 1 over omega 1 is the time required for the system to oscillate through 1 radian. Now for a lightly damped oscillator, we know that the total energy of T equal to E naught e to the power minus gamma T. So from this, the rate of change of energy dE by dt equal to minus gamma E naught e to the power minus gamma T. But E naught e to the power minus gamma T equal to E. So this is minus gamma E. So this is the rate of change. So the energy dissipated in a short time delta T is going to be the magnitude of dE by dt multiplied by delta T. So this is gamma E delta T. So this is for a delta T time interval. So now we know that 1 radian of oscillation requires the time delta T equal to 1 over omega 1. Therefore, the energy dissipated per radian is going to be gamma E multiplied by 1 by omega 1. So this is gamma E by omega 1. So the quality factor Q equal to energy stored in the system, which is E divided by energy dissipated per radian, which is gamma E by omega 1. E cancel. So Q equal to omega 1 by gamma. As I said, for a lightly damped system, omega 1 is approximately equal to omega naught. So Q is also equal to omega naught by gamma. Now for a lightly damped oscillator, we know that gamma by omega 1 is much smaller than 1. Gamma by omega 1 is much smaller than 1. Consequently, the quality factor is going to be much greater than 1. So for a lightly damped oscillator, Q is very high. And for a heavily damped system, gamma by omega 1 is very high and Q is very low. So Q is inversely proportional to the loss of energy, right? So for a heavily damped system, losses are very high, Q is very low. For a lightly damped system, losses are very low, Q is very high. So if you take an oscillator like a tuning fork, it typically has a quality factor of 10 to the power 3, whereas a superconducting microwave cavity can have Q of the order of 10 to the power 11. Q is very high. Q very high means losses are very low. That's why a superconducting microcavity is used in a resonator circuit, because especially when you are dealing with very low signal, even the slightest of the losses is going to be very crucial. So you need to have a resonator which has the minimum, the least amount of loss possible. So that's why you employ a superconducting microwave cavity in such applications. What will be the quality factor of an undamped oscillator? For an undamped oscillator, gamma is 0. Consequently, Q is infinity. So undamped oscillator has infinite Q. So that's about damped harmonic oscillator. Now before winding up the discussion, let's do a quick problem. A musician's tuning fork rings at 440 Hz. The sound level meter indicates that the sound level decreases by a factor of 5 in 4 seconds. What is the quality factor of the tuning fork? Now the sound level of the tuning fork is related to the energy stored in the tuning fork, and we know that energy stored E of t equal to E naught e to the power minus gamma t. So at time t equal to 0, the energy is E naught, and at time t equal to 4 seconds, the energy is going to be E naught into e to the power minus 4 gamma. And the ratio of these two sound levels, or ratio of these two energy levels, is 5. So E of 0 divided by E of 4 equal to 5. Substitute for these two. So E naught divided by E naught e to the power minus 4 gamma, which is e to the power 4 gamma equal to 5. From this I can write gamma equal to ln 5 by 4, which is 0.4. So Once you find gamma, you can find quality factor using the equation Q equal to omega 1 by gamma, where omega 1 is the angular frequency of the tuning fork, which is 2 pi multiplied by the linear frequency 440 Hertz. So this is 2 pi into 440 divided by 0.4, which is 700. So that's for today. Thank you.